Welcome to The Explainer. Today, we're going to tackle a question that's, well, it's at the very heart of our modern world. How do we keep our private conversations, our bank details, our entire digital lives secret? Let's break down the science of how we all whisper on the internet.
So let's just dive right in. Think about it. Every single time you buy something or send an email or even just message a friend, you're basically broadcasting information across this massive public network. So how does any of it arrive privately, meant only for the recipient's eyes?
You can almost imagine the internet as this giant room, just full of mail carriers. Your message, it passes through so many hands on its way to its destination. And anyone in that room, what the experts call an eavesdropper, could just grab it and read it. Unless, of course, your message is written in a secret code.
And that simple idea, a secret code, it brings us to our very first method. It's really the most intuitive one of all. Just a simple shared secret.
Okay, so it's called symmetric encryption. And you can think symmetrical because it's perfectly balanced. There's one single secret key, and it's used to both lock and unlock the message. If you have the key, you can read it. If you don't, it's all just gibberish.
So, for example, let's say you have a simple numeric key. That key can scramble the message. Computer science is exciting. Each letter gets shifted by a specific number, and poof, it turns into a meaningless jumble for anyone who doesn't have that exact key.
So the crucial point here is this transformation. We take our original readable message, that's called plain text, and we use that secret key to turn it into ciphertext, a scrambled, completely unreadable version. Then, the person on the other end uses that exact same key to reverse the process. Simple, right? Well, not quite.
Because this simple system, it immediately creates this giant paradoxical problem, one that almost makes the whole idea, well, kind of useless.
This is what's known as the key sharing dilemma. Think about it. To read your secret message, your friend needs the secret key, but to get them that key, you have to send it to them over the same public, insecure internet where all the eavesdroppers are listening. If they grab the key, they can read everything. It's a classic chicken and egg problem.
And this right here, this is the fundamental weakness. The security of the entire system, it all hinges on keeping that key secret. But there's no safe way to share the key in the first place. For a long, long time, this was a massive roadblock for digital privacy.
So, how did we solve it? Well, with this wonderfully clever and kind of counterintuitive idea that completely changed the game. Honestly, this solution is the reason your online life is secure today. And it's called asymmetric encryption. The breakthrough is to stop using just one shared key. Instead, we give every single user a linked pair of keys, a public key and a private key. Now, they are mathematically connected, but you could never guess the private key just by knowing the public one.
Okay, here's the absolute best analogy for this. Think of your public key as an open padlock. You can make copies of it and give it to absolutely everyone. Anyone can take that padlock and snap it shut on a message box, but, and here is the magic part, only you have the one unique private key that can actually open it.
All right, let's walk through the story of Tom and Jane to really see this in action. So first, Jane generates her two keys. She keeps her private key totally secret. Then, she sends her public key, her open padlock, to Tom. Now, it doesn't matter one bit if an eavesdropper sees it, because that key can only lock things, not open them. So Tom writes his message, puts it in a box, and uses Jane's public padlock to lock it shut. He sends this locked box back to Jane. That box is now completely secure. Even Tom can't open it anymore. Only Jane, with her secret private key, can unlock that box and read what's inside.
And right here, we can see that whole process playing out. First, Jane sends her public key out over the open internet. Then, Tom uses that very public key to send a securely encrypted document right back to her. And just like that, the key-sharing dilemma is solved.
This just brilliantly illustrates the power of the whole system.
Jane could literally post her public key on a billboard. Tom, Susan, Mike, anyone in the entire world could use it to send her a private message that only she can ever read. This is the fundamental technology that secures your banking, your email, pretty much everything you do online.
So this public-private key system is the powerful backbone of our current digital security. But, the arms race between the code makers and the code breakers, it never, ever stops. And the next battlefield, well, it's taking place on a scale that is almost unimaginably small.
The next great leap is quantum cryptography. Instead of just relying on really hard math problems, this method uses the fundamental laws of physics to create security. It's built on the strange, wonderful, and frankly bizarre behavior of particles like photons, the basic units of light itself.
So here's the core idea, and it's a bit wild. In quantum mechanics, the very act of looking at a particle can change it. So if an eavesdropper tries to intercept the photons that are being used to build a key, the simple act of them looking disturbs the whole system. The sender and receiver know instantly that someone is listening in. It's like a burglar alarm that's built right into the fabric of reality itself.
And this leads us to the final and really critical takeaway. The same quantum principles that can create these unbreakable codes, well, they might also be used to build quantum computers that are powerful enough to shatter all of our current encryption. The race is on. So the question isn't just how we whisper on the internet today, but how on earth we'll make sure our secrets stay secret in the quantum age of tomorrow.